All right, so here is chapter 9 that we're starting with today. Um, we'll be calculating a new inferential statistic T. We've calculated a lot of a previous inferential statistic called Z. We started really doing that a lot in chapter 7 on hypothesis testing. Chapter 8, which is what we just got finished, we were still dealing with Z, but we were dealing more with confidence intervals, effect size, and power in the previous chapter. So we're really building a lot of the hypothesis test stuff that we learned in chapter 7 with Z, but now we're using T. And I want to point out to you how similar this T equation is to the Z equation that we dealt with previously. And by the way, when I'm talking about Z equation, I'm talking about the Z equation where you're dealing with the sample mean, where n is greater than 1. Um, and so here's the T equation. And if you notice, the numerator of the T equation is the exact same as the numerator of the Z equation. That is, you're taking a sample mean and you're subtracting from that sample mean a population mean. So the numerator of T is the exact same as the numerator of Z. But if we look at the denominator, if we look at this stuff down here, we notice things are different. So in the Z equation, this whole thing was called standard error. But if you notice, and so this thing is called estimated standard error right here. This is S sub n. This whole thing is estimated standard error. How is this estimated standard error different, like at least as far as the exact symbols I'm using, compared to the regular standard error that we saw in the denominator of Z? How is this thing that I'm circling, how is this different than standard error from the Z equation? What's changed?
With no population standard deviation.
Yes, that's correct. We're not dealing with the population standard deviation anymore. If you recall, then this thing right here, the thing I'm circling, used to be sigma, which meant population standard deviation. What we're doing the T statistic, instead of using population standard deviation, we will now have sample standard deviation here instead. And this kind of gets at the heart of why the T statistic even exists. In actual practice in psychology, for sure, but probably most fields of science as well, it's very unusual that you will actually know information about the population parameters. By definition, the T statistic is what you calculate when you do not know the population standard deviation. However, in all practice, if you don't know the population standard deviation, you will not usually know the population mean either. But I want to point you out, so this is kind of a weird thing about the T statistic, and I'll explain how we deal with this in a second. In the T statistic, we don't know the population standard deviation, so we use S instead. But we still use mu. Mu is the population mean. We still actually use this in the T statistic. And so there's kind of this weird situation, like, why would we know the population mean if we don't know the population standard deviation? And to give you the answer, most of the times when you're doing this, the type of t-test that we're going to learn in this chapter called a one sample t-test, this mu right here, the population mean, is inferred from probability theory. And I will give you an example to explain what I mean. But for the one sample t-test, which is what we're doing in this chapter, this mu number is typically inferred from probability theory. This mu is not one that we actually arrive at by taking all of the members of the population, adding their scores, and dividing by the number of scores in the population. Because the truth of the matter is, most situations in real life, we don't actually know all of the information about the population. For instance, it's not known, the population that I study in my research is usually all American adults. And I don't usually know the music perception abilities of all American adults. And I don't know the standard deviation of that either. And so this one sample t-test is used when you don't know the population standard deviation, in which case you use the sample standard deviation instead, but you can infer the population mean using probability theory. This is one of 3 types of t-tests that we're going to do. We're going to focus on the one sample t-test today. And then next time we will get started on what's known as the paired samples t-test. And then once we get to, I believe it's chapter 10 next week, we will be dealing with something called the independent samples t-test. So we're doing the one sample t-test today. Let's break it down a little bit more. So this denominator part, when we're dealing with Z, was called standard error. Now this denominator part for the T statistic is called estimated standard error. And you can see the formula. This stands for estimated standard error is what this stands for right here, this S sub M. Whoops. And you can see this right here matches exactly what we have here. This is the standard deviation of the sample divided by the square root of n gives you the estimated standard error. And in case we forgot, we actually have calculated sample standard deviation before, this thing S. We have calculated that before. And here's the formula. So you've seen this before. Someone remind me, how is this, how is the sample standard deviation formula that I'm circling right here, how is it different than the population standard deviation formula that, how is this different than the population formula that we used back in the day? Anyone remember?
The -1 instead of just n.
Yep. Yes, you guys are both correct. N-1 is what's in the denominator instead of just n. For the population standard deviation, it's just n in the denominator. But here for the sample standard deviation right here, the denominator is n-1. So there's the question, why even do this? And the reason is because this is kind of a penalty. We don't really know the true standard error because we don't know the population standard error. So we use the sample standard deviation to approximate, to estimate what the true population, we use the sample standard deviation to estimate what the population standard deviation would be. And then we're using that sample standard deviation to calculate this estimated standard error. But this is just an estimate. We don't know the true standard error. So the reason why n-1 is in the denominator here is because this kind of penalizes us. Now I need to explain why this penalizes us. So this will take a few steps. So here's the sample standard deviation right here. And what we're doing is we're dividing n-1 is the denominator instead of n. So basically what we're doing is we're making the denominator here smaller. And when you make the denominator of this ratio smaller, what it does is it makes the overall ratio bigger. So that's worth repeating. When you subtract 1, what you're basically doing is making the denominator a little bit smaller. But when you make the denominator, when you divide by a smaller number, what that does is it makes the overall ratio bigger. So subtracting 1 from the denominator basically makes the standard deviation a little bit bigger. That's how we penalize ourselves. But the reason why this matters, the reason why this penalty matters is because then this S, it plugs into this estimated standard error equation. We have a bigger S, which means that the overall estimated standard error will also be bigger. S is bigger, which causes this overall estimated standard error, this thing which is in the denominator of the overall T ratio, the whole denominator is going to end up being bigger as a result of subtracting by that 1. And then this is something I want you guys to help me out here. If the number in the denominator here is getting bigger, how does that affect the overall T ratio? When the denominator here gets bigger, how does that influence the overall T ratio?
It'll be smaller.
Yes. As the denominator gets bigger, the overall T ratio gets smaller, which for our purposes means it's getting closer to 0. And if you think about what it takes to reject the null hypothesis, we have those distributions and we have the critical regions, which are in the tails. When we subtract this -1, it makes the sample standard deviation bigger, which makes the estimated standard error bigger, which makes the overall T ratio closer to 0. In other words, when we do this little correction, this n-1, that makes the T further away from those critical regions, closer to the center of the distribution, which basically means we are less likely to reject the null hypothesis. We are less likely to find a significant effect. So that's the primary reason for doing this n-1. Because we don't know the true population standard deviation, we have to estimate it, and we kind of give ourselves a little bit of a penalty because we are estimating it, and that penalty is n-1, which causes the T ratio to be closer to 0, which means we are less likely to reject the null hypothesis. Okay, so here's a couple little things. Probably the most important thing there's random facts around here. Probably the most important thing on this slide is this idea that, like Z, T is defined relative to a distribution of means. And what I mean by distribution of means is we have that distribution, and we're going to find those critical regions, and beyond those critical regions, we're going to find those critical boundaries, and then beyond those critical boundaries, those are the critical regions. Whereas if our test statistic, and now it's T, falls in one of those critical regions, we will reject the null hypothesis. But an important difference between T and Z, whereas Z, we always use the same distribution, the normal distribution, the same Z distribution, and it was defined based on that crazy formula that I showed you a couple chapters ago. Very long, complicated formula that we haven't dealt with was the definition of the Z distribution. When we're dealing with T, there's actually literally an infinite amount of different T distributions, and you have a T distribution for each possible degree of freedom. So the definition of degree of freedom for now is kind of scoot down here. For now, our definition of degree of freedom is just whatever our sample size is minus 1. And so if our sample size is 20, then we're going to use the T distribution that corresponds to degrees of freedom equals 19. That is 20 minus 1 equals 19. Sample size minus 1 equals 19. If we have a sample size of 40, so if we have a sample size of like 1,000, then we would use the T distribution of degrees of freedom equals 999. Whatever our sample size is, we subtract 1 from that. That's our degrees of freedom. And then we use a T distribution that is that specific degrees of freedom. We didn't deal with degrees of freedom with Z. We always just used the same Z distribution. But now with T, each sample size that we use, we're going to use a slightly different T distribution. And that will influence where the critical T boundaries are going to fall along our distribution. Yep, moving on. So this is showing the different distributions. The normal distribution, which I have, which is labeled right here, that's just another word for the Z distribution. The normal distribution is the same as the Z distribution. And we could see how for that one, which is the thin dotted line right here, it's the tallest one shown here in this picture, and it's also the thinnest one, which means it has the least amount of variability. And shown below it, here is a T distribution where the degrees of freedom equals 20. If the degrees of freedom equals 20, by the way, what is the sample size?
21.
21, you're working backwards if that's correct. So 21, if the degrees of freedom is 20, then the sample size is 21 because 21 minus 1 gives you, with sample size of 21 minus 1 gives you a degrees of freedom of 20. And so the T distribution when your sample size is 21, that is the degrees of freedom is 20. It's shorter than the Z distribution, that is it's shorter than the normal distribution, and it's also a little bit wider, which means it has more variability than the Z distribution. However, it has this middle line right here. It's taller and has less variability than this one right here. So this is a T distribution when the sample size is 6, that is when the degree of freedom equals 5. And we can see that this one is the overall shortest. And if we look at the solid line, it's also the fattest as well. So the idea of the T distribution is that as the main thing about the T distribution to remember is that as sample size increases, that is, as degrees of freedom increases, the T distribution gets thinner, 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 and thinner. As sample size, that is degrees of freedom, increases, the T distribution gets thinner and thinner and thinner. And as that sample size increases, it's gradually approaching the shape of the Z distribution. So all this matters because we are going to be using this T table right here. And this T table helps us find critical T values given 3 pieces of information. Maybe I should show you that information now. So here is, you can click on this if you're following along in the slides. This is a Google Doc that has a picture of a T table. And there's 3 pieces of information that you need to know to use this T table. One, you need to know the degrees of freedom, which you can see right here. That's shown along the side here. Remember, the degrees of freedom is just the sample size minus 1. And this shows not all possible degrees of freedom. Literally, there's an infinite amount of degrees of freedom you can have, 1 through infinity. This is just showing, it shows 1 through 30, and then it goes 40, 60, 80, 100, 1,000. So it's just kind of giving you a sampling of all the different degrees of freedom that possibly exist. That's on the left side here, the left margin. So that's one piece of information you need, the degrees of freedom. The other piece of information you need to know in order to use this is, are you doing a one-tailed test or a two-tailed test? And so if you look here, one-tailed versus two-tailed, the top line right here is the one-tailed test. The bottom line is two-tailed test. The third piece of information we need to know is what is our alpha? Is our alpha 0.05 or 5%? Or is our alpha 0.01, which means 1%? And that's what these actual numbers are right here. So for instance, well, I'll just go to an example before we actually dig into that. So that's the t-table. Let's do an example right here. So here is a t-distribution for degrees of freedom equals 3, which means our sample size is 4. So we have a small sample of 4. We're using an alpha of 0.1, which means our alpha is 10%. This is actually an alpha value, which in psychology at least is very uncommon. I don't think I've ever seen a published study with this, but nevertheless, it's a potential alpha that could exist mathematically. So our alpha is 0.1, which means alpha is 10%, and we have two tails. So if alpha is 10% and we have two tails, that means 5% is going to be in this left tail, and 5% of the distribution is going to be in this right tail. But we have these critical boundaries right here, and these are the numbers that you can get from the t-table. So we need to know these three pieces of information: degrees of freedom equals 3, alpha equals 0.1, two tails, and now we're going to go to our t-table, and we're going to look up the critical t value for that set of values. So our degrees of freedom is right here. If I can make this bigger, I don't know if I can. Yeah. So our degrees of freedom equals 3, which is right here. And we're using two tails, so we're going to use the bottom line up here. And it said alpha equals 0.1, which is right here. So we look where those connect. Here's two tails, alpha equals 0.1. And we go to where it connects with degrees of freedom equals 3, which is right here, 2.353, right here, 2.353. And now let's go back to our slide. And you can see it says negative 2.353 and positive 2.353. So when we have a t-distribution where degrees of freedom equals 3, that is our sample size is 4, alpha equals 10%, we have two tails. The critical boundaries, that is the t values, which mark the critical regions, which are these shaded areas, are these two plus or minus 2.353. If we then calculate a sample t and it falls in these critical regions, one of these two critical regions, we would reject the null hypothesis. So we'll do some more examples of using the t-table, but first I want to give us an example of the actual one sample t-test, which is what we're performing in this class. The one sample t-test, what we do, I've kind of described this a little bit, we are comparing some sample mean to a number, and what that number is a hypothetical population mean. It's hypothetical once again because, well, it says right here, the hypothetical population represents chance performance. We don't actually, and when we're using the t-statistic, we don't actually know the population standard deviation. And in real life, if you don't know the population standard deviation, that means you're also not going to know the population mean. But there is a set of circumstances in which we can infer using probability theory what the population mean should be. And that is exactly when the one sample t-test is used, when we can infer the population mean based on probability theory. So we will calculate a sample mean, and then we will compare that with a hypothesis test to a hypothetical population mean to determine whether there is a significant difference between a sample mean in this hypothetical population mean, which is inferred from probability theory. So yes, we will do an example, and that is here is the example right here. So this is a common paradigm in studying infant behavior, is to look at the amount of time they spend looking at things, because infants can't talk and they can't push buttons on a computer screen. So if you want to measure infant psychology, the most common dependent variable is the amount of time they spend looking at things. And you want to see, do the infants look at different objects a different amount of time? Do they have preferences for certain types of objects? And you can infer a preference in infants if they spend more time looking at an object compared to another object. So a common way of doing this type of study will be give infants two objects. In this case, in this example right here, the two objects that the infants are looking at would be two faces on a computer screen, one of which is attractive and one of which is unattractive. And both faces appear on the computer screen at the same time. And those two faces are shown on the computer screen for 20 seconds. And at any given point in time, you, the researcher, depending on whether the eyes are closer to the attractive face or the unattractive face, at any given point in time, the baby is always judged as being looking at, he or she is either looking at the attractive face or he or she is looking at the unattractive face. Whichever face the eyes are closest to, you score that the baby is looking at that face. So it's always looking at one of the two faces for the entire duration of the 20 seconds. And the question that is asked here is, does the baby spend more time looking at one of the faces compared to chance performance? And so we have to kind of use probability theory to make a guess. How long would the baby spend looking at each face if the baby showed no preference at all? So what I'm trying to do is figure out, it asks here, what is the null hypothesis? And remember, the null hypothesis basically is the baby doesn't show a preference for either face. The baby looks the same amount of time to one face as it looks to the other face. There is no difference. There is no treatment effect. It doesn't matter whether the face is attractive or not. The null hypothesis says the baby should spend the same amount of time looking at the attractive face as it would the unattractive face. And so if the baby is looking for 20 seconds, and that means that if there's no effect, that the baby should spend 10 seconds looking at each face. And so I've written that, the null hypothesis, right here in the notes portion. So you should check it out in the notes portions if you can't read it very well. Right here, I'm highlighting it. The null hypothesis would be the mu of the attractive face. The amount of time that the baby spends looking at the attractive face would be 10 seconds. And we need to kind of figure out how this 10 seconds was derived. The answer is that there's 20 total seconds and there's two faces. If there's two faces, then 50% of the time the baby should be looking at each of the face. 50% of 20 is 10 seconds. And so the null hypothesis is the baby does not show a preference for either face. Then the null hypothesis is that the baby should spend 10 seconds looking at the attractive face, which, yes, a mathematical corollary of this is the baby also spends 10 seconds looking at the unattractive face. But the way the null hypothesis is worded, we're just talking about the attractive face. The amount of time spent looking at the attractive face is 10 seconds. That is half, that is 50% of the total length of the trial, which is 20 seconds. The baby should spend 10 seconds looking at the attractive face. The research or alternative hypothesis then would be shown right here. The amount of time that the baby looks at the attractive face is not 10 seconds, which if you look at this clearly, this research hypothesis implies a two-tailed test, because when we say the amount of time looking at the attractive face does not equal 10, that can mean two things. Either the amount of time looking at the attractive face is greater than 10 seconds, or the amount of time looking at the attractive face can be less than 10 seconds. So those are the two tails. One tail is the baby spends more than 10 seconds, which would be way over here looking at the attractive face. Or the other possibility is that the baby spends less than 10 seconds looking at the attractive face, which would be over here. So we have our null hypothesis, where the amount of time looking at the attractive face is 10 seconds, and our research hypothesis, which is the amount of time looking at the attractive face does not equal 10, which is implying a two-tailed test. Okay, so going back to do some mathematical examples here. Here's our example. A couple things about this example. We're going to assume that we've collected data from 9 babies. So if we've collected a sample from 9 babies, our degrees of freedom will be 8. our sample mean is 13. What this means is that the amount of time when we actually collected data from those 9 babies, the actual mean amount of time that those babies spent looking at the attractive face was 13 seconds. I'll say that again. The sample mean M is 13, which means on average, those 9 babies spent 13 seconds out of the 20 looking at the attractive face. The sum of squares which is part of the standard deviation calculation was 72. Back in the day, if we were in class, I would have made you use this to calculate sample standard deviation, but instead I've just calculated the sample standard deviation for us 3, and I will show you how I did that on the next slide. So the sample mean is 13, the sample standard deviation is 3, and I'll show you how I calculated that. We need to calculate the estimated standard error. I will also show you that as well, and we need to calculate the t statistic. So let's go ahead and do all of those things right here. So here is our sample standard deviation. This 72 is the sum of squares. The denominator is n minus 1. Our sample size is 9. And so 9 minus 1 equals 8. 72 divided by 8 equals 9. And then the square root of 9 equals 3. So that's how we got the sample standard deviation. And I want to remind you of where we got that formula for. So here is the formula for sample standard deviation I showed you at the beginning of class. Sum of squares divided by n minus 1, or if you expand sum of squares, this is the same thing. This is just the sum of squares right here. So here's the sample standard deviation equals 3. But remember, when we're calculating t, when we're calculating estimated standard error, the thing which is up here is no longer sigma, it is S. That is, it's no longer the population standard deviation. We are now using the sample standard deviation. So that's why you see the number 3 here. The number 3 is here because that's what we calculated the sample standard deviation to be. We're dividing by the square root of n. N equals 9. So the square root of 9 is 3. So 3 divided by 3 equals 1. So our estimated standard error is 1. And then now we can plug that into the t equation. So t equals, this 13 right here is our sample mean, which is m. Once again, this is the amount of time that the babies on average, those 9 babies, on average, they spent 13 seconds looking at the attractive face, minus 10. This is our hypothetical population mean. This is the thing that was inferred using probability theory. Once again, there was 20 seconds, 2 faces. So the null hypothesis says the baby should look at each face the same amount of time. If there's 2 faces for 20 seconds, that means the baby should spend 10 seconds looking at the attractive face. The sample mean was the babies actually spent 13 seconds looking at the attractive faces on average. The hypothetical population mean inferred from probability says that if there was no effect, the baby should spend 10 seconds looking at the attractive face. So this is the numerator. M minus mu gives you 3 divided by, it's kind of hard to see, I know, down here, but this is the estimated standard error, 1. So 13 minus 10, 3 divided by 1 equals 3. So our t value for this problem is 3. So let's kind of go back and reassess. So yeah, I've showed you how we calculate the standard deviation. The sample standard deviation equals 3. The estimated standard error, I showed you how that equals 1. That's what this S sub m is. That's the estimated standard error. The t statistic that we calculated is 3. Now what we need to do is perform the actual hypothesis test. We need to determine, is that t that we calculated 3, is it in the critical region? And so I'm going to give us 2 little problems. We're going to first do a problem where the alpha is 0.05, and then we'll do another problem where alpha equals 0.01. So if the critical region, so we're doing alpha equals 0.05, what we need to do is we need to go to our t table and find what is the critical t when we have degrees of freedom equals 8. We're doing a 2-tailed test, which I've made bold here. And alpha equals 0.05, what is our critical t value? So let's go do that. So going to our t-table right here. Um, degrees of freedom equals 8, just on the left side. We're doing a two-tailed test, so we're going to use these numbers right here, up here, and we're looking for, what is it, 0.05 is our alpha level. So we go to where those meet, and right here it says our critical T is 2.306. We're doing a two-tailed test, so that's plus or minus 2.306 is our critical T values. So we need to determine, is our T value of 3, we calculate our T value right here, here's 3, is that in our critical region? And I'll show you once again. I kind of worked this out and wrote it here. If alpha equals 0.05, that is 5%, and we have two tails, and our degrees of freedom equals 8, the critical T value, according to the T table, is plus or minus 2.306. The T value that we calculated was 3. So the question is, are we in the critical region or not? Is our T value of 3 in the critical region or not? Can someone answer that for me?
Yeah.
It is. Can you explain how you knew that? Like, what's your justification for that answer?
If the mean 0 and critical T values 2.3, 3 is greater than 2.3.
Exactly. The sample T that we calculated, 3, is greater than 2.306. Therefore, we're in the critical region. I've drawn a picture, one of my beautiful artwork pictures. By the way, I uploaded this picture into the slides like 1 minute before class. So if you downloaded the slides before class, you might not have this picture, but it's in there now. But here is the picture that we could draw. So negative 2.306, that's the critical T. Positive 2.306 is right here. That's the critical T. Our T value that we calculated was 3, which I drew the arrow. That's where it would go. Right here, this would be the shaded region. This is the critical region. So, oops. So 3 is greater than 2.306. Therefore, T of 3 is in the critical region, in which case we would reject the null hypothesis. So when we use an alpha level of 0.05, we would get, going back to our answer here, or our problem, the sample mean of 13 is significantly different than the hypothetical population mean of 10. 13, they were looking at the attractive face, significantly longer than chance performance of 10 seconds. That's assuming that our alpha level is 0.05. But now let's do an example where our alpha is 0.01. So remember what this alpha means. Alpha means the total amount of area which is in the tails. When alpha equals 0.05, that means there's 5% of the area is in the two tails. When alpha equals 0.01, that means that there's now only 1% of the area in the two tails. So 0.5% is in the left tail, 0.5% is in the right tail. you add those two numbers together, and that gives you 1%, or alpha equals 0.01. In order to get 1%, basically what you're doing is you're moving those critical boundaries further into the tails, further away from the center of the distribution. That's what alpha equals 0.01 is doing. It's moving those critical boundaries further away from the center of the distribution, further into the tails of the distribution. And so now we need to use our t-table. And the answer is going to be this. So if alpha equals 0.01, and it's two tails, alpha equals 1%, two tails, degrees of freedom equals 8, the critical T is going to be 3.355. I'll prove that to you by looking at right here. Degrees of freedom equals 8. Now we're using two tails, but alpha equals 0.01. So we're using 0.01 right here. Go down to where it says degrees of freedom equals 8. And this number that I'm circling with my mouse is 3.355. 3.355, which is exactly what I had written here on the slides for you. And so this is the critical T we have if alpha plus or minus 3.355, if alpha equals 1%, if alpha equals 0.01. So the sample T that we calculated is still 3. But now if we choose alpha equals 1%, well, you tell me, are we in the critical region? Is T equals 3, is that in the critical region or not?
No.
It is not, and I'll just go ahead and show you now. Here would be the reason why. So if degrees of freedom equals 8, 2 tails, alpha equals 0.01, our critical t's are these things right here, negative 3.355 and positive 3.355. The center of the distribution would be right here. That's where t equals 0. And you can now see that our t value that we calculated is inside. It's in the middle portion now. It's not in the tails. It's not in the critical regions. And so we would accept the null hypothesis. That it was, we'd say there is not a significant difference. If we choose alpha equals 0.01, this t-score of 3 is not far enough away from the center of the distribution that we would call it a significant effect. When alpha equals 0.05, we'd say, yeah, we have a significant difference. But when we make the alpha more strict, that is when we say alpha is 1%, then this number 3 does not fall into the critical region in which we do not have a significant effect. Yeah, that's actually, we'll do the one-tailed examples next time. So I can answer questions about this right now, or you guys can take off, and we will continue on with t-tests next class.